In this video lesson, we are going to look at Theorem 325. Now, also just to remind you once again how we do mathematics, so make sure that you understand all the steps, not only of the examples, but also of the theorem's proofs that we are going to be working through. And then also when you see the pause button, make sure that you pause the video and do the sums on your own. Just watching through this is not going to help you as much as actually doing the work. And then when you've done it, just make sure that you mark your work as well to see where you make your mistakes. Okay, so an overview of this is we're going to look at Theorem 3 and its application, and then Theorem 4 and its application, and then Theorem 5 and its application. So for Theorem 3, 4, and 5, the first section is about looking at the theorem itself and also looking at the proof, how to do the proof for that theorem, and then the application is basically where we applied in questions that we can is exam-like questions. Although, like I've said in the previous video as well, the questions in this video is not as complex. It's basically just focusing on each of the theorem on its own, just to get you into the habit of using each and every theorem, so it is a bit easier than what you would normally expect for exams. So Theorem 3 says that the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at any point on the circumference of the circle. So just to look at what they are saying here is the arc that they are referring to is KL, this arc. Now, you can either think about it as an arc or maybe as the chord. And then when you connect these 2 points to the center of the circle, those 2 lines form an angle in between them, all right? And then when you follow these same 2 points and you follow it through to a point on the circumference, you'll see that it forms a second angle over there. So basically what Theorem 3 says is that the angle that forms at the center will be double in size as the angle at the circumference, okay? And normally in exams or in more complex questions, it won't be this obvious. It can be a bit more complex where we have different other lines on the diagram running between these. So what I do initially, what helps me, even if I follow it like physically with my 2 fingers, like following it up from those 2 points to the center and also following it up from those 2 points to a different location or any other point on the circumference, just to identify that this is the theorem that's applicable. Alright, now when you use this theorem, this is the reason that you give. The angle at the center is 2 times the angle at the circumference. And then to look at the proof. Now, this theorem specifically, there are 3 separate ways or 3 separate diagrams that it can look like. So this is the first one we saw, which is the basic one. Then it can look like this, which basically just means that this angle is twice. So this angle is twice as big as this angle. So it just looks a bit different, but it's the same concept. Now, when we do the proof, I'm going to focus more on this one. And then for the third diagram, we're going to do in the next part separately. Okay. Now, what are we given? We are given that O is the center of the circle, very straightforward. And we are given that J, K, and L are points on the circle, also very straightforward. Alright, now what do we need to prove? So we need to prove that KOL, which is this angle over here, is twice KJL, which is that angle over there. Now, first of all, what we're going to do is we're going to construct this line. So in this diagram, the line OJ looks like that, and in this diagram also OJ, which just looks like that. Now, before I go ahead, I'm just going to give you a heads up of what we are aiming for or what we are working towards. Okay. Now, we are going to name J1 and J2 X and Y. Okay. And then we are going to find all other angles in terms of X and Y until we can find KOL in terms of X and Y and see if we can make that relationship where this angle is twice that angle. Okay, so you'll understand that a bit better when we've done it. Now, in your proofs, when you are examined on it, you do not need to make, the only thing you need to do on the diagram is to show that, to show this construction. Okay. And then you have to do the working out, which we are going to do over here. But I'm also going to make notes on this just to show you what's happening over here. Okay, so the first thing we do is we let J1 equal to X, and we let J2 equals to Y. Okay, and then we note that OJ, OL, and OK is all three are the radius, which means they are equal. And our reason is radii, so all three of these are equal. This leaves us with two triangles. So one over here, JOL, and this is a isosceles triangle, okay? And also the other triangle, JOK, also an isosceles triangle. So therefore we can also say that K is equal to X, and that L is equal to Y, because of equal sides is equal angles, equal sides. Okay. Next up, we can also find O2 and O1 in terms of X and Y, because we've got now angles of a triangle. So for O1, if we add up all the angles of a triangle, it adds up to 180. So O1 in terms of X is then going to be 180 minus 2X, and O2 in terms of X is going to be 180 minus, in terms of Y is 180 minus 2Y. Okay, and then we can find this angle, because now we can use angles around a point to find this angle, and KOL is then all of this 360 minus this angle, and then just simplify that expression. So that simplifies to 2x plus 2y. If we factor out the 2, you're left with x 2 times x plus y. And we've seen that this angle over here is x. The two adjacent angles are x and y, so together they are x plus y. And now we can see that KOL is 2 times x plus y. So for any value of x or y, this angle will always be double that angle. So we can say, therefore, it's twice JKL. Okay, and that is basically the entire proof over there. So next up, we have the same proof, but this time the shape of our diagram is different. It's more like the bow type kind of shape. And now, again, we just need to prove that O1 is double J2 over here. All right, so we're going to start off with basically what are we given, what do we know? We know that O is the center of the circle, straightforward enough, and JK and L are points on the circle. All right, now what do we need to prove? We need to prove that KL, once again, is 2KJL. Okay, now the construction that we're going to make is again OJ, but obviously that looks a bit different than the previous one. Now what we're going to do is we are also going to name two angles, 1x and 1y, and then find all of the other angles in terms of x and y, and see if we can get the relationship where J2 is half of O1, or O1 is twice J2. So the first thing is we're going to let J1 equals to x and J2 equal to y. And then once again we notice that OJ, OL, and OK are all equal to each other because they are the radii or radius. And this once again forms two isosceles triangles. So one is OJL and the other one is OKJ, which means that we can say that this angle over here is equal to K. So K is equal to X, and also that this angle over here, this entire angle here, J1 and J2 is x plus y, so that means L is also x plus y. Okay, and then we are going to say that O2, so we've got this triangle, so O2 is then equal to 180 minus x plus y minus x minus y, and to simplify that we get 180 minus 2x minus 2y, so that's this angle over here. Now next we can find O1 or KOL in terms of x and y. Now that's quite a few things to take into consideration. Now we've got 180, then minus this O2, which is this entire part here, okay, which you see here, minus this angle x minus this angle x. That leaves us with this angle over here. And if we simplify that, it basically simplifies to 2y. And that basically proves that this, if this is 2y and this angle over here is y, kjl, then we can say for any value of y that kol is 2 times kjl. And then we have done our proof of theorem 3. Okay, now the corollaries that form. So when you have like when the arc is basically the semicircle, right? That means that this is your diameter, which is 180. So if the angle subtended is always half, so the angle subtended to the center is always half when it's subtended to the circumference of the circle, that would automatically make then a 90-degree angle whenever you subtend an angle from the diameter of a circle. Okay, so that is basically what this says. The diameter subtends a right angle at the circumference of the circle, meaning it looks like that. Okay, and so this is something that I've seen a lot in questions, and it's easy to miss, but whenever you see an angle subtended from the diameter, it is basically a 90-degree angle. Okay, and then also if the angle at the circumference of a circle is a right angle, it is subtended by the diameter. So sometimes you're given the opposite. Sometimes you are given that it's a right angle, but you're not given that it's a diameter. So you can make that you can make that conclusion when you know it's a 90-degree angle. You know that it's subtended by the diameter. And the reason you use this angle in semicircle. Alright, so that was the first section where we have the theory for theorem 3. Let's look at some practice questions. Okay, example 3, determine the size of B. So this is pretty straightforward, quite easy, because we know that the angle at the center is twice the angle at the circumference. So that makes B then equal to 90 if that is at the center. So B is equal to 90, and then you just need to know your reasons, obviously, off by heart, and that is just angle at center is 2 times angle at circumference. So angle at center is 2 times angle at circumference. Then for question 3.1, we see that O is the center of the circle, and we know that the HK is then the diameter, and the diameter always subtends 90-degree angle, so A is equal to 90 degrees, and the reason is angle in semicircle. Okay, then question 3.2. Now this JH subtends to the center of the circle, and that's C, and then it also, from the same 2 points, we can see it follows through to K, which is 20. So we know that C is 40 degrees, because the angle at the center is twice the angle at the circumference. Okay, and that's it. Then determine the size of D. Okay, this just is in a different shape, but D again is twice that angle. So D is equal to 200 degrees. Again, angle at center is 2 times the angle at the circumference. Then for 3.4, determine the size of E. Now there's quite a number of ways we can do this, about 3 ways we can do this. But let's just look at what we have. This is the center of the circle, and then we've got a 30 degree over here, we've got E over here. And remember, the radius also is always the same. the radius is OJ, OH, and OK, which immediately makes it possible for us to find this angle because they are in this isosceles triangle. These two angles are equal. Also, this is also equal to E, all right? And then we also know that this is the diameter which extends a 90-degree angle. So this is then 90 degrees. Okay. Now, that's the one way we can now say that E plus 30 is therefore 90 degrees and so for E. Okay. But what else we could have done is, even without saying that the radius are equal, we could have gone straight ahead and said, okay, this is 90 degrees, right? Because it's subtended by the diameter, and then we can just use angles of a triangle. So E plus 90 plus 30, that is equal to 180. So either one of those two reasons. I'll just go with the second one. I think it's just a bit faster. So we can say JHK is equal to 90 degrees. So angle in semicircle. Semicircle. All right, and then we can just say, okay, E plus 90 degrees plus 30 degrees is equal to 180. So that's angles of a triangle. So now to solve for E, we just take the other two to the other side. So we've got 180 degrees minus 90 minus 30. And that will give us E is equal to 60 degrees. Right, then for question 3.5, determine F. Now, with F, if we have this angle over here, we know that this angle is double KHJ or F. All right, so to find that angle, we can use angles around a point. So we can say that KOJ is plus the 120 degrees is equal to 360 degrees. So that's angles around a point. And then we solve for KOJ by saying it is 360 minus 120. So this is 240 degrees. Okay, so if this is 240, we know that it's double F. So F is then equal to 120 degrees. And our reason is angle at center is equal to 2 times angle at circumference. Circumference. All right. And that was theorem 3. Next we move on to theorem 4. So theorem 4 says that the angles on a circle subtended by a chord of the circle on the same side of the chord are equal. So meaning if we have this chord or arc, PR, then we can follow it through these 2 points and they both connect to M, and then the same 2 points followed through connect to N. And basically what that means is wherever it is, even if it's like over there, all of these angles subtended by the same chord are equal to each other. Okay, and if you use this, you are going to say angles in same segment. That's the reason that you use. Now for the proof, we are given that M and P and R are points on the circle. We are also given that O is the center of the circle. What we need to prove is we need to prove that M is equal to N. Now this proof is very short and very easy, simply because we are going to use theorem 3 that we already know, and we're going to use that in this proof to just basically prove that M and N are equal. We're also going to make a construction. So the construction that you're going to make is OP and OR, all right? And we know that this angle, so we can see that this now is an angle that's subtended to the center of the circle. We know already that this angle is 2 times the angle at the circumference. So if we know that this angle is twice N, and we know that this angle will also be twice M's size, then therefore M and N must be equal. And that's basically all that we're going to say in this proof. So we're going to start off and say that POR is 2M, okay? this is the POR, and then we're also going to say that POR is 2n. All right, with our reason angle at center is 2 times angle at the circumference. And then we're going to say, but therefore m is equal to n, and that concludes our proof. So this is very short and simple because we can use a previous theorem to in our proof. Okay. Now corollaries: equal chords subtend equal angles at the circumference of the circle. So if I have two chords any place on the circle, but they must be equal to each other, and then whatever angle they subtend, those two angles will always be equal. Okay, so when the chords are equal and they subtend different angles, those two angles will also be equal. And you can use the reason equal chords subtend equal angles. Now the converse of this theorem: if two angles subtended by the same line are equal, then ABCD is a cyclic quadrilateral. So basically all we know in this is that angle A and angle B are equal. Okay, and if we know that they are equal, that means that this quadrilateral must lie in a circle, making it a cyclic quadrilateral. So basically this is just the theorem in reverse, if you want to think about it like that, because either with the normal theorem we know that this is a this is subtended, you know, like this is a cyclic quad, we can see that, but because it's subtended by the same chord in the normal theorem, we know that the angles are equal. But the reverse of it says, if you don't know that it's a cyclic theorem, but you do know that the angles are equal, then you can deduce that it is a cyclic quadrilateral. And the reason is, again, angles in same segment. Alright, so now going on to the application. So for example, determine the size of A. Very straightforward. We can say that A is 21 degrees, and our reason is angles in the same segment. Okay, and then going on to question 4, determine the size of X. Now basically we can see that this chord CB is equal to AB, and that makes the angles that they subtend equal. So we can say that X is equal to 15 degrees, and our reason is equal chords subtend equal angles. Right, so for example 5, in this case we can see we've got two parallel lines. NQ is parallel to OP, and therefore we can apply alternate angles. Okay, so we can say that OQN is also going to be 17, and then we can see that this NO subtends to Q, and it also subtends to P. Therefore D is equal to 17. So I'm going to start off and say that NQO is equal to 17 degrees, and my reason is alternate angles, whereas NQ is parallel to OP. Okay, and then I'm going to say that D is equal to 17, and this is because the angles are in the same segment, so angles in same segment, and that's our answer. Then for question 5.1, again notice the parallel lines, right? And then also see that HI is subtended to G, HI is subtended to F, HI is subtended to E. So all three of these angles are basically equal to each other. All right. But now from what we are given this angle over here. So what relationship do we see? We can use our parallel lines, obviously, to see that this is also 15 because it is alternate angles. Okay. So I'm going to start off and say that HFI is equal to 15 degrees, whereas we've got alternate angles and FH is parallel to EI. Okay, and then we can say that B is equal to 15 degrees because they are angles in the same segment. Now for question 5.2, given that ZX is perpendicular to WY, calculate the size of F. Alright, so ZX runs there and XY over there, and they are perpendicular, forming a 90-degree angle. Okay, we want to calculate F. Now just to look at a few things that are equal, we can see that this subtends, this XY subtends the 35-degree angle. It also subtends this XZY, so this must also be 35 degrees. Okay, and this is F, so this must also be F. Okay, so that's just a few things that we can see immediately, because WX subtends this angle, and it also subtends the angle WYX. Okay, the other thing that we can see is that this is the center of the circle. O is the center of the circle, so ZX subtends this angle ZWX, so that means it's a 90-degree angle. Okay, and this one also a 90-degree angle. Okay, now I think that's all that we can see so far. Now how can we solve for F knowing that? Now if we have this as 90 degrees, therefore we can solve for ZWY. Okay, so that would just be 90 degrees minus 35, so that would give us 55 degrees. We also know that this is also a right-angled a right angle, so that makes a right angle triangle, or we have then one unknown in this triangle, so therefore we can find F like that. Okay, so let's just write down what we did. So we've actually found a lot more on here than what was necessary, but we'll just write down the necessary things. First of all, we saw that ZWX is 90 degrees, so ZWX is equal to 90 degrees, and that is because the angle in semicircle. All right. Then we can solve for this angle. Since we know that ZWX is a right angle, we can say that ZWY, so ZWY plus 35 degrees is equal to 90 degrees. Okay, and this just follows from the previous one. We've just basically replaced ZWX with its two adjacent angles. So this is going to be ZWY is equal to 55 when you say 90 minus 35. Okay, and next we know that this is a 90-degree angle, so we can use angles of a triangle to solve for F. So you can say F plus 55 degrees plus 90 will be equal to 180, and our reason is angles of a triangle. And then to solve for F, this is going to be 180 minus 90 degrees minus 55 degrees. So I think that brings us back to 35 degrees. Then for example 6, R, S, T, U, and V are points on a circle with diameter RU. Calculate the size of angle SUV. Okay, now what do we know? Those are all points. We want this angle, and this is a diameter. So first of all, when we know this is diameter, it subtends a 90-degree angle over there, and we have these angles over here. Now we can see that this arc over here subtends up to R 45, but it also goes up from here, it goes up to here, so this is also a 45-degree angle. And then the 35 degrees, we can see it subtends to there as well. Okay, so I'm just trying to look at a few things that we can use to solve. Now the other thing is that we have this 12 that also subtends from SR. It subtends up to the 12-degree angle. It also subtends up to this 12-degree angle. Okay, and now we actually have the one side of the angle we want. So if we can find this side, then we can add them together and find SUV. Okay, and we can see that this is a triangle, and we can use angles of a triangle there as well. Okay, now let's actually start and just say that this angle is 12. So we've got SUR. So SUR is equal to 12. Okay, and then it is subtended angles in the same segment. Okay, and then we saw that because this is the diameter, it subtends a 90-degree angle over here. Okay, so we can say that RVU is equal to 90 degrees because it's angle in semicircle. Okay, and finally we can say that RUV plus the 35 plus the 90 will all add up to 180. RUV is plus the 35 plus the 90 is equal to 180, and that's angles in a triangle, or angles of a triangle. And then just solve for RUV. Okay, so that's 180 minus 90 minus 35, so that's going to give us 55 degrees. Okay, so if this is 55 degrees, then we can just conclude and say that SUV will then be equal to 12 degrees plus 55 degrees, and this will then give us 67 degrees. Alright, then for question 6.1, calculate the size of X and Y. Okay, we have this, alright, that is 88, and it's AB subtended to the center of the circle. AB is also further subtended up to X, okay, and there we can see immediately what X's value is going to be, because the angle at the center is twice the angle at the circumference. So we've got that X must be equal to 44 degrees, and our reason is angle at center. We can also write, instead of writing the word center, we can write angle at center is equal to 2 times angle at circumference. I think that's a bit easier. Okay, and then we need to find Y. So basically we've got BC that subtends Y, but BC also subtends O1. Right, so we can find O1, it's easy to find Y, and this AOC that forms the diameter, so that basically these two angles lie in a straight line. So to find O1, we can just say, okay, angle O1 plus 88 is equal to 180 because it's angles on a straight line. Okay, and then therefore angle O1 is just 180 minus 88, so that gives us 92 degrees. Okay, so this makes it 92, and then we can say, okay, but therefore Y is equal to half of that, which is 46 degrees, and again our reason is angle at center is 2 times the angle at the circumference. Okay, then 6.2. We want to find the calculate the size of X. All right. Now, what do we note? We note that we have the angle of 35. We also see that QP is equal to RS, meaning the angles that they are going to subtend are going to be equal. So what does RS subtend? RS subtends P2. It also subtends X. Okay. This makes this also X. You can just include that. Then we see that QP is subtend R1. So whatever RS subtend will be equal to what QP subtend. So if this is X, then this must also be X. Okay. And then we can actually immediately see our solution, because we now have angles in a triangle. Okay. So we've got, the first thing we did was that saying that R1 is X. So R1 is X, and that is because they are equal chord subtend equal angles. So equal chord subtends equal angles. Okay. And then we can say that x plus 35 degrees is equal to 180 degrees, and this is angles of a triangle. And then just solve for x. So 2x is equal to 180 minus 35 degrees. Okay, so that gives us 145. So 2x is equal to 145, and then divide both sides by x. So x is then going to be 70 plus 2,5. So that is going to be 72,5 degrees. Okay, so theorem 4 is done. Next we move on to theorem 5. Now theorem 5 says that the opposite angles of a cyclic quadrilateral are supplementary. So what does that say? Supplementary means they add up to 180. So meaning the opposite angles U and T are opposite angles, so they must add up to 180, and then also S plus V is supplementary, they must add up to 180. So if you ever use this, this is the reason: opposite angles of a cyclic quad. Okay, and to look at the proof, once again we are given that S, T, U and V are points on the circle, and we're also given that O is the center of the circle. Now what we need to prove is we need to prove that T plus U is 180, and we also need to prove that S plus V added together will give us 180. Okay, now the constructions that we do is going to be OS and OV. Alright, then what we're going to do is we're just basically going to name this angle X. Okay, and then we're going to kind of see if we can find U in terms of X, and do they add up to give us 180, right? And then once we've done that, if these two add up to 180, it means that because of a quadrilateral adds up to 360, we know that if these two add up to 180, the other two must add up to 180 as well. Okay, now like I said, first thing we do, we let T equals to X. So I'm just also going to make those notes here. So X, and then we know that the angle at the center is 2 times the angle at the circumference. So that means that O1 must be 2x if that is x. Okay, and then we can use the angles around a point to find this angle over here. So this is going to be 360 minus 2x. So this is 360 minus 2x because it's angles around a point. And then we can say that this angle here subtended would be 2 times this angle over here. So that would make SUV or 2U. So that would mean that O2 is twice U. Angle at the center is 2 times the angle at circumference, and that means if we divide this by 2, we get 180 minus x. Okay, now what we do is we're going to say what is T plus U. So we've got this side, we've got 180 minus x, and this side we've got x, and if we add these two together, they simplify to 180, and therefore we've proven that they will also always add up to 180 regardless of what the size of x will be. And then since S plus V, or since T plus U adds up to 180, we can say, okay, S plus V must be 360 minus T plus U, and that basically is 360 minus 180, and that leaves us then with 180. Okay, and that is basically the proof. Right, so now the corollaries. The exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. So what happens is, if I extend this line, okay, then an angle over here forms. But what happens is this angle, these two angles are angles on a straight line, and angles on a straight line add up to 180. So angle C plus this angle will add up to 180, but also we know that the opposite angles of a cyclic quad also adds up to 180. And this then means that that angle over there must always be equal to B. So the exterior angle of a cyclic quad is equal to the opposite interior angle. And we use the reason exterior angle of a cyclic quad. Okay, and then the converse. A cyclic quadrilateral is a cyclic quadrilateral if the opposite angles are supplementary. So if we know one of two things, so if we know that C plus B is 180, or if it is true that A plus D is 180, then that means that this quadrilateral will lie in a circle, meaning it's a cyclic quad. So a lot of times they will ask you perhaps that you need to prove that this quadrilateral is a cyclic quadrilateral, and this is the other proof that you can use. You can try and prove that the two opposite angles add up to 180, and therefore you conclude and say that it is a cyclic quadrilateral. And this is the reason opposite angles of a cyclic quadrilateral are supplementary. Okay, so theorem 5 is done. Now only to do the application and the sums. So example 7 says calculate the size of A and B. Very easy, because we know now that these opposite angles are supplementary. So we know that A plus 87 degrees is equal to 180 degrees, and we have our reason that says that it's just opposite angles of a cyclic quad. So opposite angles of cyclic quad, right? And then we just basically solve for A. So A is 180 minus 87, so that gives us 93 degrees. And the same with B. B plus 106 degrees is equal to 180 degrees. So again, opposite angles of cyclic quad. Okay, so B is equal to, so this is going to be same as 80 minus 6, so this is 74 degrees. Right, so question 7.1, calculate the size of A. Now, first of all, we can use these two angles, which are opposite angles. They add up to 180, and find W, and then we can use angles of a triangle to solve for A. So I'm going to say that W plus 86 degrees is equal to 180 degrees. This is opposite angles of cyclic quad. Okay, and then W must be equal to 180 minus 86, so that's the same as 100 minus 6, so that's going to be 94 degrees. Okay, and that is then 94 degrees. Then we can say that A plus 94 plus 57 degrees is equal to 180, and this is angles of a triangle, and then A is equal to 180 minus 94 minus 57. Okay, and for that I'm going to use the calculator. So this is 180 minus 94 minus 57. Okay, so that's 29 degrees. Okay, again, calculate the size of A. This is very easy because we know that the exterior angle is equal to the opposite interior angle. So A is simply going to be 114 degrees. And our reason is exterior angle equals interior opposite. So exterior angle of cyclic quad. Okay, calculate the value or the size of x and y. So now we have 2x over here and 3x over here, but we basically just going to go ahead and use our relationships that we know. We know that this angle, whatever it is, must add up with this one and form 180 or give us 180. So I'm just basically going to say that 2x plus 3x is equal to 180, and my reason is opposite angles of a cyclic quad. And just go ahead and solve for x. So these two add together, they give us 5x equals to 180. And then if we divide both sides by 5, 180 divided by 5 will give us 36 degrees. And then the same for y. We've got 2y plus y is equal to 180 degrees, opposite angles of cyclic quad. Right, and that gives us 3y equal to 180. And if we say 180 divided by 3, that gives us 60. So y is equal to 60 degrees. And then for 7.4, calculate the size of x, y, and z. Now let's start with x. So if we look at A, B, C, D, that's a cyclic quad, and the opposite angles are 50 and x, so they add up to 180. So x plus 50 degrees is equal to 180 degrees, opposite angles of cyclic quad. All right, and then that makes x equal to 130 degrees. Okay, now for y, now we can see that this is the center of the circle, and this subtends the angle y, which means y is 90 degrees. Y is 90 degrees, angle in semicircle. All right, next we've got z. Now z is just the third angle of a triangle, so you can use angles of a triangle. So you can say z plus 90 degrees plus 50 degrees is equal to 180 degrees, angles of a triangle, and solve for z. Z is then 180 degrees minus 90 minus 50, so this gives us 40 degrees. Okay, 7.5. Again, solve the size or calculate the size of x, y, and z. And again, we've got x here, but we can see this one's actually easier because this is the exterior angle, 125, and x is the opposite interior angle. So x must be equal to 125 degrees, exterior angle of cyclic quad. All right. Then to find y, again we can see that this is subtended by the diameter, so y is equal to 90 degrees, angle in semicircle. Okay, and then to find z, now we can see that this triangle ECB has an exterior angle, and with triangles, the exterior angle of a triangle adds up to the two opposite interior angles. So we can say that z plus 90 degrees is equal to 125 degrees, and this is exterior angle of triangle. Okay, and then z must be equal to 125 minus 90. So let's just do that. And that gives us 35 degrees. And then question 7.6, calculate the size of x and y. All right, so here we've got an exterior angle. We've got angles that are subtended over here. And we've got angles that's subtended from QP. So we've got a few things that we can take into consideration. But now first, let's focus on x. And we can see that this angle is the exterior angle, which is equal to the opposite interior angle. So you can see that this entire section here must be equal to that one over there. So x plus 40 is equal to 70 degrees, which is the exterior angle of cyclic quad. Alright, so x is then equal to 30 degrees. Alright, and then what we can do is we can similarly say that this angle here must be equal to this 80 degrees angle. Now the only thing we short is this angle over here, and we can see that QR subtends the 30 degree angle, but QR also then subtends QSR. Okay, so QSR is also 30. So I'm going to say that QSR is 30 angles in same segment. Right, and then we can do the same. We can say that y plus 30 degrees is equal to 80 degrees because it's the exterior angle of cyclic quad. Okay, and then solve for y. So y is equal to 50 degrees. Alright, so that was the last section, and then we are finally done.